Today we're going to discuss the design validation by analysis we performed on a Cubesat using the MSC Apex application for finite element modeling and finite element analysis. So we'll start with introductions. Tentacle LLC as a services company and also the solutions we provide. MSC Software and MSC Apex and the MSC One token system, which is important to discuss since this is the products that we use for this validation. Next, we'll actually look into the actual validation of the system, going from mechanical specifications to the actual practical application of finite element modeling and analysis to solve some design problems or ensure that the design is properly adequate for the mechanical specifications. Then we'll finish up with a couple of remarks on the actual system and how it worked for us in an extension to further analysis that we could do thanks to the MSC One token system. Tentacle LLC as a company assists aerospace and defense industry in designing better, safer products, faster at a reduced cost. We do this by extensive use of finite element analysis, modeling and simulation, as well as other tools and methods that we apply. Personally, I am the CTO and director of the company, co-founder as well. We have started a little bit over 6 years ago, and we have grown steadily since then at a double-digit pace every year. I manage the technical aspects of the company mostly, which includes tool selections, tool usage. I manage naturally projects and customer relations, as well as the analysis team of the company. I come from the aerospace and defense industry, mostly in Europe, which is now called the Airbus Group. Used to be Eurocopter, used to be Aerospatiale. Worked on different things, helicopters, rockets, ballistic missiles, in the stress and dynamics groups, performing stress analysis at the part level, assembly level, system level, under different capacities. Tentacle LLC as a company is an ITAR registered woman-owned small business. We are located in Los Angeles with a field office in Billerica, Massachusetts. We perform modeling and simulation for our customers. We are considered and usually brought on as subject matter experts in those areas. We deal primarily with rugged electronics, defense electronics, RF and microwave components, or systems. We perform structural dynamics, shock and vibration, thermal design, and electronics cooling for customers, although we perform other things such as vibroacoustics or design for reliability analysis, MTBF analysis, and those different aspects. As far as industry distribution and our expertise, about 70% is in the defense electronics and 70% in the shock and vibration. No surprise. This is what we do for a living, so it's actually a good thing that we do most of what we do for a living. Second most important contribution is thermal and CFD. So we do a lot of thermal electronics cooling analysis. And we also perform some CFD, being external aerodynamics or aeroacoustics, and those type of analysis. Now moving on to MSC Software. MSC Software was one of the original software companies in the US, one of the first 10 companies. They were started following a NASA contract to create a unified structural analysis tool for NASA. This was about 50 years ago, and this is how Nastran started, and this is what is now MSC Nastran. MSC Nastran is probably the most renowned FEA code in the world, and this is trusted across industries by many. along with MSC Nastran. MSC Software also is considered the pioneer and the top provider of software in other areas. MSC Adams, for instance, rigid body dynamics, MSC Mark, nonlinear analysis, CINDA, thermal analysis, including especially very strong thermal analysis for satellites and spacecraft, and MSC Actron, which is vibroacoustics analysis. And there's many more applications, and one of the interesting things about the portfolio from MSC Software is everything resides in a token system. So at any point in time, you can access one or more of the different products. You're not limited to one or two products that you have purchased. So this is very important, and we'll talk about that later. And lately, in the last few years, 4 or 5 years, MSC Software has decided to bring something new to the table. And they've called it MSC Apex. And this is a world's first in the CAE world in terms of how the system deals with analysis results and simulation in general. It brings naturally high performance pre and post processing, but also an interesting new way and new innovation in the world of finite element analysis that actually brings a lot of value. And so this is called computational parts, which we'll discuss a little more in detail. So the MSC Apex is a CAE platform. It's actually remarkably easy to learn and to use, and our users have picked it up in a couple hours. And when you compare that to a high-end system equivalent, because don't mistake Apex for a simple application. This is complex, capable application for doing complex modeling and complex analysis. So if you compare that to one of the other high-end systems, it takes weeks to get used to and be proficient with those systems. Well, MSC Apex is probably more a matter of hours, worst case a couple days. This already brings a lot of value to us. All users were up to speed in a day. Other things that are very interesting in this systems are all the tools for geometry abstraction and simplification. Naturally, we deal with a lot of CAD data. Very rarely is it in a native CAD manner that we can directly address in our CAD system. Quite often we get step files or neutral files of any sort, and it always is a battle to remove features, change geometry, simplify geometry. Well, with MSC Apex, the tools are there to actually address this and directly impact the meshing process by being able to modify, tweak, defeature native geometry of any kind. On top of it, there's some very good meshing algorithms and a very strong mesher being brick meshing, TAT meshing, shells, beams, 2D, 1D elements, you name it. And lastly, the integrated solver, which is called generative, meaning that as we progress, as we make changes, as we add things, the results update. This is a very new way of dealing with FEA data, FEA results, in the sense that computational parts, which are parts from an assembly, hold the results for themselves, meaning that an assembly of parts is practically solved beforehand because the results of each part is contained in the parts. So there's only a little assembly that has to be done, and the results are processed very quickly. And we'll see that, we see that in the next slide, in fact, the time difference between standard processing and this computational part. So the typical structural analysis is of an assembly, for instance, is I do my assembly meshing, I put my loads, my boundary conditions in my assembly, I hit the solve button, I wait 10, 5 minutes, 2 hours, it depends on what kind of solution I'm processing. Now I get my results, I figure out there might be some issues with the design. I might want to look at, what if scenario. I make my modifications. I resolve. I wait the exact same amount of time. Well, MSC Apex does slightly differently. MSC Apex is creating this analysis results at the part level, meaning that if I have 100 parts, I have results from my 100 parts. Now, if I'm modifying one part, I don't need to reprocess the other 99. I'm resolving only for the difference, so which speeds up the solution quite a bit. On average, we see a 2.5x, and quite often it's more than that. We'll say on average. So the first solve might take an hour, the second solve will take 20 minutes, and incremental solves will take 20 minutes. So as you're doing what-if scenarios, you'll notice that you gain 20-40 minutes every time you solve for a what-if scenario. So it is very possible, and we see that every day, that you've run 5, 6, 7 iterations in a day instead of 2, maybe, or even sometimes just 1, depending on the size of the problem. So big time compression simply by using this incremental model validation and solution. Now let's see how we apply that to the Cubesat that we had. So we're going to look at requirements, the environments, how we solve those, and how we got our results. So the first thing is, well, what do we have to look at with a Cubesat? Well, there's 2 things. Actually, there's only one. Really, the CDS from Cal Poly San Luis Obispo. So the Cubesat design specification tells me how big a Cubesat needs to be, the interface points, how much it can weigh, and all this. And then it tells me, well, you have requirements for photo flight and acceptance testing. So why don't you go look at the GSFC standard 7000, which is coming from NASA Goddard. And this contains the general environment coming from the launcher, coming from the launch adapter, coming from the environment in general for a certain number of things. We're going ourselves to limit the study to mechanical, being stress and vibration and shock. So the list, if you want, of things that we have to look at start with a model survey. So what you don't want is your Cubesat to resonate with the launcher at any point in time. You don't want the excitations to be amplified, and because that'll be catastrophic, the Cubesat will fall apart. So you want to conduct a very thorough model survey and have a good understanding of the model characterization of your Cubesat before you do anything else. And coming from that, we will be able to already tell if we're going to have issues or not with shock and vibration, simply by saying, well, based on my model survey, I'm going to avoid the peaks, or I'm going to be right under them, or I'm stiffer than the load would be resonating at. So we're going to see a lot of those things, and also structural loads. I mean, there's simple acceleration loads. There's all of this to look at, and sign vibration and shock and all this. So the way we started, we start with a CAD assembly, which is the natural way of doing things these days. We have a 3D model, and this one is in CATIA. It was designed in CATIA, so this 3D model, the assembly is there, sub-assemblies, all the parts, all the components, all of this presented there. So the first thing we want to do as analysts is we want to review this. We want to reuse all of this. We don't want to recreate anything. So we bring that in directly in Apex. We bring the CAD assembly natively, file open or file import, CATIA. Boom, we get the CAD product in there, and the assembly, the geometry, the product structure, the positioning, even the colors, everything shows up in place. And the naming convention, of course. So very, very interesting, very useful. The assembly structure, sub-assemblies, the parts, everything is maintained. Now, the second thing, once we get that, what we want to do is do a first pass at cleaning up the geometry. I'd say cleaning up is really removing the things that we don't really want to include in your analysis. Tiny fillets, small holes that don't really participate to the structural strength of the system, and would cause some grief with the meshing pass, meaning we'll have a lot of small elements because the mesher tries to fit into those small little features. They don't bring any value for analysis. They're just going to hinder us a little bit by creating too many elements in locations we don't care about. So Apex has a really, really nice set of tools to do a first pass quasi-automatic, remove all the fillets smaller than 0.01 inches, for instance. Remove the chamfers, remove this, remove that. So we clean up the part, and at any point in time, we have a visual feedback of what's happening. So we're not blindly removing things and turning all complex geometry into a simple cube. We're actually seeing what we're removing, and we can actually select and refine the selection, or decide to preserve things even though they're small, but they might be of interest. So all of this is very interactive and very powerful. Again, on a geometry that is CATIA geometry. So we don't have a CATIA feature tree or CATIA running inside. We don't need to be in CATIA to do that. So very, very useful. Next, we create the meshes. So we mesh at the assembly level directly on the part, directly on the geometry. Again, we have a extensive array of element types that we can use, and which is actually a good thing, because this Cubesat actually has a large array of different things in there. Some are modeled with beams or springs or solid elements, shell elements. Some can be brick mesh. They're more in the shape of a prism. Some cannot be brick meshed, so we use TED mesh for that. So automated TED meshing or detailed brick meshing, and on top of it, we have a lot of tools to connect disjoint meshes, being at the edge, at the face level, that allows us to create very detailed meshes, for instance, of those components, lead wires that we want to look at with solid brick elements. And we don't necessarily want to have a large amount of elements on the component case itself, but we want to have a fair amount of elements on the lead wires to actually represent bending properly. So we're able to do that and connect them automatically with what's called glue joints. Same thing for the fasteners. Fasteners are created with beam elements, a combination of beam elements and rigid elements. We control the cross section, the material, the positioning, and rightfully we can recover fastener loads at those components, at the fastener connections, and we can go and do calculator bolt joint calculations and margins later. So the first step was a model survey. So a model survey is a classic model analysis. Constraint modes or rigid body modes, both can be run and are run with a certain range of interest. So the range of interest in this case is up to 2000 Hertz for a certain launcher. And what the outcome of this is not only the resonant frequencies, so that's a given. We want to know what's our first mode, second mode, etc. What also we are presented with is the list of mass participation factors, which highlights the dominant modes in a particular direction. And this is very important for us to simplify or to analyze the system in a quasistatic acceleration equivalent, to know that they are dominant modes. So for instance, in a particular direction, I'm going to have 80% of the mass moving in this direction at the same frequency. So this is my list of dominant modes, my list of mass participation factors that MSC Apex solver actually gives me. Also gives me a effective mass fraction total of my frequency range. So if I'm saying I want to be able to represent typically 85% of the structure without modal truncation, I'm presented with this amount of modes, and I can use residual vectors if I wanted to augment that as well. So, but first outcome is to give us, a good idea of how much mass is moving at what frequency, and how much within 2000 hertz, how much of the structure we're really representing dynamically. Now, on with this, we can very easily create some conservative first pass evaluation loads for shock and vibration. And again, this depends on the model results. This would give me, assuming 50% of the mass is moving at 300 hertz, for instance, for this little call, we can say, okay, based on that, let's use a Miles equation for random vibration. This gives me a peak 3 sigma acceleration to apply, and this is going to be very conservative, but this is a first pass design validation. And similarly, we can use Harris shock and vibe formulas to actually get an equivalent shock pulse of the same type of quasi-static acceleration. Now, if you want to go a little further, this is fine and dandy to have a quasi-static acceleration. No, sometimes we predict 200-300 Gs quasi-static acceleration in those very conservative manners, and this is not at all what happens in real life. There's a little more scattering than this in the dynamics environment, than simply everything moving at a particular frequency. So for this, we actually can go to dynamic response into MSC Apex to do both time and frequency domain. So we could do both. Typically, we use frequency domain. Again, we can select how many modes to keep. We can select residual vectors to augment that, to increase the accuracy of the results. We certainly control modal and structural damping. And interestingly enough, we can also do inertial relief, which in all cases is actually useful for something in flight or in space. And as far as the response or the results that we get, that is the standard peak stress, displacement, acceleration forces, forces in the fasteners, the modal contribution, which is very handy to have, and also all the transmissibility and transfer functions. So we actually are able to predict and know the response of, say, the center of the top component, and to get this transmissibility and see if there's amplification and where, and so on and so forth. So very useful, very easy. And once again, all this is performed in the context of the analysis parts. So meaning that when I change one part and I rerun, again, I'm rerunning only a fraction of the solution. The rest is contained in the part and maintained as such. Now, once we get all those results, peak stress, peak displacement, acceleration, now we get to, and peak forces, we get to look at, standard bolted joint calculation. So NASA TM 106943 is an example of what we use, and using those fastener forces that we recovered from MSC Apex, we plug that directly into calculations for joint separation, slippage, bolts, margins for tension, shear, bending, or even combined, and also thread shear. So we can do all this very easily. The data is created by Apex, and all we have to do is plug the little equations that are pretty standard. Similarly, we also wanted to look at, especially in the context of random vibration, we wanted to look at fatigue of the components. So the possibilities for the lead wires and the solder joints to crack under vibration. For this, again, the main piece of data that we need is provided by MSC Apex. So we get a Steinberg approach to fatigue calculation, which actually requires or needs the maximum normal deformation of the board in the center of the board, and from there we can calculate, back calculate and evaluate fatigue limits for each of the components based on the type of components, based on the location on the board, and so on and so forth, and the frequency of the frequency of the event. And that allows us to calculate a number of cycles to survive, and compare that to the number of cycles that the components will see during flight, and that allows us to calculate a safety margin or fatigue life evaluation. So, in closing remarks, what we have done with MSC Apex was actually very fast, from learning the product to creating the models to get the results we wanted to verify and validate the design, to running multiple design iterations. Let me change a web thickness, let me move a connector, or move a fastener around, resolve in a fraction of the time. All this was very, very impressive, and I'd say, based on our experience, we gained 30 to 50% on our delivery time by using smart applications like computational parts, and being able to provide a fast mesh and fast analysis results to this project was, of course, accelerates the design and allows us to deliver faster. Now, it's not all finished. Now, there's a lot more to do in terms of, for instance, mission profile, random vibration, fatigue, downstream applications such as the actual orbital thermal analysis, so the Cubesat in action, if you want, or even the vibroacoustics on the launch pad in the launcher. So all this needs to be done. This is not necessarily done inside Apex. Apex has a finite amount of functionality at this point, but there is a way out, and the way out is within MSC Software. So the way out is actually reusing the models that we created. So we're not losing anything, we're just augmenting the model. So bringing it directly into Nastran, into Cinda, so we can bring the model directly in Cinda, put it in orbit, and calculate all the orbital heating and all this. Vibroacoustics, same thing. So we do that, and we have actually done this with other larger projects. For instance, we have an example there of it's a giant telescope. This one was started in MSC Apex, and because of the MSC One licensing, we were able to provide more functionality, being fluid structure interaction, CFD, thermal, thermal expansion, acoustics. So there was a lot of applications that we were able to perform. The starting point being always the model created in MSC Apex. So if you'd like to know more about us, or ask us questions, or simply peruse or list of applications or what we can do, there's a lot of ways of connecting with us. I mean, the easiest way is a website, naturally. Then the traditional means of interacting nowadays, so Facebook, YouTube, Twitter, LinkedIn. YouTube would present a lot of applications. The ones we can display, naturally, there's a lot of working in the aerospace and defense. There's a lot of things we can't show that are much, much cooler than what ends up on YouTube, but we can't show it, unfortunately. Facebook and Twitter have a lot of activity as well. So there's a lot of entertainment that can be provided from our web pages and in our network. Thank you very much, and hopefully we'll hear from you soon. And if you have any questions, again, contact us directly on our website.